Yes, thank you. Firstly, I would like to thank organizers for giving me a possibility to be here today. I will be speak about. Firstly, I will say what is the spin noncommutativity. Later, how it influences on such quantum system as hydrogen atom, and then using our result, we estimate an upper bound for the parameter of noncommutativity. Noncommutativity was widely investigated after this paper, where Zyber-Convita shows then noncommutativity can appear on brains. This algebra, including this coordinate commutator, is so-called canonical noncommutativity. It has some problems. Firstly, it lacks non-locality, it violates microcausality, and the biggest one is in such things that canonical noncommutativity is not invariant under spatial rotation. Rotation invariance can be restored in noncommutative algebra by using against of constant theta, something more complicated. And if we will use a function of dynamical variables and additionally spin operators, rotational invariance can be restored. Historically, first such algebra was proposed in this paper. Their constant was replaced by this value, and the following algebra is obtained algebra is the following. It is easy to find representation of such algebra. Momentum is not deformed, but coordinates is shifted by spin operators. Small letters denotes dynamical operators which satisfy ordinary algebra. The other one was proposed there. If we start from the Bob shift for canonical noncommutativity and replace theta mu nu by this thing, in fact, Pauli-Lubansky pseudo vector, we obtain an algebra with the following coordinate commutator. Of course, such thing as noncommutativity may appear at Planck scales, but also it can be effectively appears in the other problems. For example, in Bose condensate, using spin noncommutativity, it is possible to explain a triplet Cooper pairing mechanism. Spin noncommutativity appears on canonical quantization of twistors, and in considering motion of Fresnel electron in Coriolis spacetime. This algebra also has something which can be called as minimal length. It can be proved in the following manner. It is well known from quantum mechanics that average of operator is not less than its minimal value. So for this algebra with this representation, it is easily to find minimal length in which is equal to this value, and for a three-dimensional reduction of algebra which was present on previous slide, we can introduce three-dimensional analog of Pauli-Lubansky vector and also find a minimal length which is equal to this. Hydrogen atom was already studied in noncommutative spaces. In the case of canonical noncommutativity, it was find a correction to the Hamiltonian, which remains spin orbital coupling, but with replacing spin by such value, which is defined by this formula. Also, hydrogen atom was studied in space with with spin noncommutativity with this representation, and here we obtain truly spin orbital coupling. We study hydrogen atom in space with such kind of spin noncommutativity. Traditionally, we postulate Hamiltonian of hydrogen atom by changing in ordinary commutative Hamiltonian dynamical variables, but by its non-commutative analogues, and obtain the following Hamiltonian. This problem cannot be solved exactly, so let us use perturbation theory to find a correction to the spectrum. We can expand this term into the Taylor series and obtain the following and rewrite the Hamiltonian in the following matter. Here H0 is equal to this operator. It's a part of commutative hydrogen atom plus one additional term, and here will be our correction. This formula is not exact, it's already approximation. So this Hamiltonian we can solve exactly. Solution can be expressed using hypergeometrical function as spherical spinors. The correction to the ordinary commutative hydrogen atoms can be found in the following way. Here J is a half integer number, and plus minus corresponds to different quantum levels. And as in ordinary commutative problem, is an integer number. This correction are good, but not in the case of S levels. It is easy to see that if we put here J equals to 1/2 and choose the sigma minus, it corresponds to the S levels. Correction diverges because of this term. It means that our perturbation theory do not work for S levels. To catch the correction to S levels, we develop a modified perturbation theory. Firstly, this idea was proposed in this paper. An idea is in the following. We will expand into the Taylor series, not in the origin, not near the origin, but in the vicinity of a point which is shifted by the origin. In every problem, its point can be used in different manner. So, in our case, we can rewrite our initial Hamiltonian as such a sum. H0 is the same H0, and perturbations can be rewrite as follows. It is an exact result. Then we can rewrite in this form, and it will be our start point. So we will expand into the Taylor series in the vicinity of such point. It is more convenient choose than the other possible expansions. So when we will calculate within the perturbation theory corrections to this problem, we can here write that this average will be average of sum. Then we can change an order of summing and averaging, and calculate such integrals. These integrals can be calculated in terms of integral exponent and derivative from it. And finally, we can obtain the following corrections to the s levels of hydrogen atom. It's interesting that here we obtain logarithmic corrections to the spectrum, which cannot be found using ordinary perturbation theory. Using this result, we want to estimate an upper bound for the parameter theta. It can be done in the following manner. Let us use results of measurement the hydrogen 2s, 1s transition frequency, and say the following magic words. Commutative theory coincides with experiment very well. So if noncommutativity exists, influence of noncommutativity cannot be bigger than error in measurements. Using this sentence, we can write the following inequality, and from here find the upper bound for parameter theta. It is not so small as Planck length, but quite well. So our results are the following. We find the corrections to the energy level of hydrogen atom in space with spin noncommutative, where noncommutative coordinates are defined by the following way. Corrections to the levels with orbital quantum number with non-zero orbital quantum number was found within the ordinary perturbation theory. To catch a correction to the s levels, we develop and use modified perturbation theory. It is interesting that corrections are logarithmic, and estimation of an upper bound was for parameter of noncommutativity was made. Thank you for attention.
Thank you. Questions or comments?
Just a mathematical curiosity. In the last formula, the correction with logarithmic correction, yeah. No, there is another one with a series dn. Dn, I think. This one. So you have calculated this dn from the expansion in the power series expansion, right?
Yes.
Okay, so you can get values. You can calculate the value. So d1 is just.
Yes, I have an expression for d1, but it is big, and
yeah, okay.
I decide not to reproduce here.
Okay, so if there are no more questions, let's thank the speaker again.